Hello and welcome back to the series in which I teach how to build CPUs in Scrap Mechanic. In the previous video, I covered the basics of RAM using D-latches. If you don't know what I'm talking about, I recommend watching the entire series of videos. The link is in the iCards. In today's video, we're going to discuss the basics of the CPU itself, specifically what instructions it will need to do. Before we dive into the specific instructions that a CPU can perform, it's important to understand some fundamental concepts that are necessary for understanding how a CPU operates. Instructions are the name of the basic tasks that a CPU can perform. Examples can be in moving or modifying data. A list of every instruction that a CPU supports is called an instruction set. Parameters are the specific values or data that an instruction operates on. Operations are actions that a CPU performs on the data, such as addition or moving around. That's the same thing as instructions. Registers are special storage locations within the CPU that hold data and instructions temporarily as they are being processed. For example, the CPU I built is 16-bit and it has 16 operations, which are numbered 0 through 15 in binary. The parameters are 6 bytes each, and there are 2 of them. This way, each instruction fits nicely in 16 bits. The way it turns a binary number to 16 separate instructions is through the use of a binary coder, which was discussed in the first video in the series. Essentially, all CPUs do is move and modify data. In this video, we will focus on the instructions that modify the data. The first instruction I'll be talking about today is addition. Quite simply, it takes the number from 2 registers and outputs an added result to a register. The adder I used was discussed in the first video in the series. How it works, in short, is A plus B. That's really all you need to do. You could have instructions such as RAM address plus RAM address plus register, register plus parameter number, also known as increment. The next instruction is inversion. Let's say you have the binary number 5, which is 101. Inverting that would result in 010, which is 2. Inversion can be useful in various situations, but it's especially important for performing subtraction. How you would build this is from your register, you would put all the bits on NAND gates or NOR gates. It's because Scrap Mechanic does not have plain NOT gates. And then you add a little bit of delay, and you write that back in your register. Now, I'm going to build it. So you start with a register. I have an 8-bit one here. Now, I'm going to use the number from example, which was 5. And now, 5 is in the register. Now, to invert this, what you would do is first, from your input, you want to, well, it's not on the input, but first you want to connect your output to a row of logic gates, and you want these to be one of the inverted types, NAND or NOR, preferably. Since there's only one type, since there's only one input, it should just act as an inversion gate instead of a normal NOT gate like you would use normally if Scrap Mechanic had them. Then you want to hook them up to a row of AND gates. And this row of AND gates will be coming from your input. Just like this. Now, from connecting all these up, you're going to want to immediately hook them back into this one, which I will do, but I'll show you why that's a bit of a problem. There needs to be some delay. But, first I'm going to show you what it looks like without the delay. So, I hook up our button. Oh, that's right. And then, I like to add another logic gate here and then put that back into the confirm write pin, just because it's got to be the same delay. And look, it flashes. It's not good. So put 5 back in, and after you've seen that, you now probably have guessed that you need to add delay. Now I do this with timers, so that's what I'll be doing next, after I disconnect them. So now I've gone ahead and disconnected it. I rearranged it a little, and I have the output going into an inverter, and the inverter going into a line of AND gates, plus an additional one, which connects to all the other ones. Now, you're going to want to put these 9 on timers on about a 6-tick delay. So I'm doing that right now. That's not 6. This is probably one of the most boring things to do, changing a row of timers. And also it's not fun to troubleshoot, because there's always one timer that seems to be off. Alright, now I hook up the logic gates into the timers, and then you can run the timers back to your input. Now this register here could be your main system register on the CPU itself, where everything goes to, and this would just act as one of the possible operations for it to do as invert. So now when I push the button, an inverted result goes through, and inverts of 5 would be 2, but since there's a bunch of zeros out front, those change to 1s. It's important to talk about in subtraction. Now, what I also like to do is I like to add a simple output on it, and since it takes about three ticks to write it, I can take 3 ticks out of that and then put it back to the output. So now it tells us when it's done. Now, you may have noticed I just have a button. Preferably you'd want a standard pulse length so that it doesn't flash. But you can see the inverter works. And it also outputs the done signal here. Now, an odd thing you might see me do is just connect up this output. It's not really odd, because CPUs need to know when it's time to do a specific operation, when that operation requested is finished. Since this instruction doesn't have any parameters, you would just send the output into where this button goes, and then the output would just send to your, what I call the done pin. That will be discussed in a future video. The next thing I will talk about is subtraction. To perform subtraction using an adder and inverter, we need to first find the inverse of the number we want to subtract. Then we add 1 to it. This is known as the 2's complement of a number. Now, you would not touch the first number. You'd only subtract. You only do this to the number you're subtracting from it. For example, let's say we want to subtract the number 7 from the number 10. In binary, 7 is 1, 1, 1, and 10 is 1, 0, 1, 0. To find the 2's complement of 7, we invert the bits and add 1, which gives us all 1s, and then 0, 0, 1, which is also known as negative 7. Then we add that plus the binary number 10, and we get 0, 0, 1, 1, which is 3, which is correct. By using an adder and inverter this way, and by representing negative numbers using 2's complement, CPUs can perform subtraction. Now, another way to understand this is in base 10. This also works. You can flip the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and for example, you convert 0 to 9, 1 to 8, 3 to 7, and so on. There will be a video about that soon, don't worry. But it's an interesting way to explain the concept of 2's complement. That will be coming soon. Bit shifting is another important operation that allows us to shift the bits in a number to the left or right. This can be useful in a variety of situations, such as quickly multiplying or dividing a number by the power of 2. For example, bit shifting the number 8 to the left by one position would give us the result of 16, which would multiply it by 2, going left once. Bit shifting can also be used to align numbers for comparison, or to extract specific bits from a larger number. Overall, bit shifting is a useful tool for manipulating and working with binary data on a CPU. The bit shifting instruction itself has 4 possible ways it could go, which could be specified by the first parameter, or they could be 4 separate commands. You can go left and right, as specified earlier, but left and right can also be done with or without rollover. An example of rollover and what it is in a hypothetical 4-bit system, the number 1 would look like 0001. If you shifted this to the right without rollover, it would just become all zeros. But if you had rollover and chose to go right with rollover, it would instead be 1000, or 8, wrapping the data around to the rightmost bit and cycling around to the leftmost. To showcase bit shifting, I will be using the same example as earlier, which was 5. Now, in your hypothetical scenario here, this is an 8-bit system, and this is the register that we're going to be bit shifting on. Now, in this example, I'll be doing left with rollover, because it's pretty easy to describe. Now, bit shifting and inverting are actually kind of simple in the way they look, and you'll see why in the end. So we are going left with rollover. So we take the first bit and we put on the second we put on third to fourth to fifth, sixth, seventh. But on the 8th, we go back around to the first. That's the rollover. If you wanted to do it without rollover, you wouldn't do that. It would just be not connected to anything, and the first one wouldn't be connected to anything either. And now, if you were doing right, I'll show that now. Right, you would just go to the right 1 bit instead. And then if you had rollover, you'd wrap around the first to the last. And you can see how that would look already. But for the actual operation, you wouldn't just put it right into a timer. What you would do first is you'd have your input button, as discussed earlier. Well, actually, I do want that. And then it'd be connected to all 8 logic gates, so that only the output of this is let through at the correct time. Like this. Right? Only the buttons press it allows the data through. And then you'd put your timers with it's probably 6. 6 would be good. 6 ticks of delay, as just like the inversion did earlier. And then you put, oh wait, that's right. So we're going left with rollover. This one is for the right signal, it's not the actual data. So you start here, right? And then you'd wrap it around since it's left with rollover. And then you put that back to your input, just like so. Now, this command could be triggered by the correct parameter in the command, or, like I said earlier, it could be its own command. So now, when I press this button, we should see the number 5 be shifted over, or multiplied by 2 and turned into 10, as it is there. Let's say you want to multiply it again, turn 10 into 20. There you go. That is how it works. Thank you for joining me in this video on the basics of CPU instructions. We covered the fundamental concepts of instructions, parameters, operations, and registers, and then explored some specific instructions such as addition, inversion, and subtraction, and bit shifting. I hope you found this information helpful and now have a better understanding of how a CPU and scrap mechanic operates and what it is capable of doing. In the next video, We will continue to delve deeper into the world of CPUs by exploring more advanced instructions and concepts. We'll also look how to build a CPU that is capable of executing these instructions and performing more complex tasks. If you have any questions or comments, please leave them in the comments section below. Don't forget to like and subscribe to stay up to date on the latest videos in this series. Thanks for watching, and I'll see you in the next video.